So good morning, everyone. Today is October 8, 2020, and today is lecture number 16, Digital MOS LSI Circuits. So this particular topic, logical effort, is actually kind of, you can say that it's also part of delay only. The logical effort, it's all about finding the delay. Okay. The problem is what is generally happening. Let's assume that there is a circuit which is like this. I'm drawing R and C because we know that most of the time whenever any MOS transistor is there, there will be resistance and capacitance. We are not adding inductor with the fact that there are no inductive effects. But at very high frequency, it might happen that you will have inductor. But for a time being, let's assume that RC are there and you are giving V in. You know that input is like this, but the output is actually delayed like this. But as you are increasing this, if what I do instead of this, if I add a big capacitor over here, then this output might look like this one, right? So it might happen that when it reaches to the logic 1 category, so this is logic 1, this particular part, so this is logic 1 and this is logic 0. In between might be the undefined state. So logic 1 and logic 0, before reaching to logic 1, if the input changes like this, then your output may not reach the maximum, but it might be like this. So you cannot define this waveform as logic 1 and 0. So you need to make sure that it reaches logic 1 and logic 0. And this is happening because of the fact that extra load has been added over here. And there is some sort of electrical effort required for the circuit to be taken into account. Electrical effort is the one which is C out with respect to what CL you have considered. So that ratio is actually defining the electrical effort. And the effort which makes sure that how much load my particular gate can drive, that is the logical effort, or it will guarantee that my output will reach logic 1 and 0 efficiently. So that is the characteristic of inverter. Let's say you have this inverter which has this is the minimum one. Let's assume that this is the minimum one. So maybe I can make more clearer that 2 times W by L divided by N, that is the W by L of P. I'm taking 2 times just to make sure that both the resistances are equal, and 2 is coming from the fact that what is mu N divided by mu P. That ratio is actually deciding this. Generally, like the book which I am following, Rabe, they are taking 2. Some books are following 3, and if you have run the Semica in 130 nanometer, we found out it's 1.55. So this is just a number just to start with, but for the different technology, this number might be different. Okay, so you need to find out that. So if this particular numbers are given, let's assume that this is 1 micro divided by 220 nanometer, and this is 2 micro divided by 220 nanometers. Look, this is very small transistors. These are not very big. Note that in 130 nanometer, if you are having the minimum size means maybe sorry, not 220, it has to be 120 nanometer. For 130 nanometer, the minimum is 129. So it's according to the plus or minus delta L. So this is given by the DRM. So for the minimum size, which is around 200 nano by 100 nanometer approximately, for this one, the capacitance offered by the transistor is around 2 femtofarad for the technology of UMC 130 nanometer. So when you will come here, you will see that we have UMC 130 nanometer, which is one of the popular one. So in that case, it's 2 femto. You can understand that this number is 5 times what this number has given to me. So it's 10 femtofarad is actually the capacitance from here, and similar for here, maybe around 20 femto, right? So the whole thing is, when you are doing this, it can drive just in the range of 20 and 10 femto. So if I connect connect an inverter right after the first inverter, as we understand that the capacitance offered by this one is around 20 femto, and this one by NMOS is 10 femto. Same for here, provided that the W by L are equal. Like here, I assume that it's 1 micrometer by 120 nanometer. Same for this one, and I assume that it's 2 micrometer by 120 nanometer for both these transistors. So when this inverter is driving this one, it's still fine because the capacitances are equal. So as per the maximum transfer theorem, you can drive the same load. However, if I change it to double, means instead of this, if it is 4 micrometer by 120 nanometer, and like, or maybe bigger than this, let's say 100 micrometer by 220 by 120 nanometer, and this one is around 50 micrometer by 120 nanometer. This cannot drive it. If you look at the output at this point, it cannot drive. When I'm saying it cannot drive, means it's going to be like this, or even worse than that, right? And it's not reaching the logic 1 and 0 are here, expected logic 1 and 0 are here, right? So in that case, first of all, like if you want to fix it, the easiest way is you can add a driver circuit. In digital, driver is just chain of inverter, but note that if you are keeping equal size of inverter, still the problem remains same. So the sizing needs to be tuned, or you need to find out what W by L has to be given. So to achieve the required logical effort or the electrical effort, you need to make sure that the sizing is such a way that it can drive the required load. And the whole process of this thing is actually the logical effort. So we need to find out that, and for that I am following different book. So this is Weston Harris, which has the chapter number 4, name is delay, and we have to understand the 4.5, which is logical effort of path. Although same thing is given in Rabe also, but very like it's a short description, and it's very quickly has been given. So if you want to understand this, by the way, there is another book is also there, which has only just logical effort. It's known as Sutherland. By the way, this is the gentleman who gave the approach of logical effort, and this is also known as Sutherland approach. So some people name it with his name, Sutherland approach. So if you want, like, his book is also available. You can refer that if you want, but there are almost like 15 chapters only on logical effort, starting from the RC, and then you are going further, and like, so, but this is very important part of any digital circuits, because most of the time such problem will occur that you are driving the next stage, and that stage you are not able to drive, because most of the time this is not going to be the case, but case might be like this that after inverter, like I'm using this maybe to many places like this. So look, so this inverter has to drive so many things. Can you see? All the capacitance looking into different direction are going to be in shunt. So then the small inverter cannot do that. or maybe other gate, like let's assume that it's just an NAND gate which has 3 inputs. It may also not drive it if you are not make sure that what is the sizing. So W by L is very important. And for that, we need to find out what W by L can drive the required load. So all such things we are going to do it in this particular topic, which is known as Sutherland and Sutherland approach, or the logical effort, where we have to go through many small things, and after building up, we can find out the required things. Note that like many of people are working just on this logical effort. Means they are doing the research, they are taking the PhD also. So it's not a small topic, and along with that, it's also the most important topic also, so that you can understand this to the part, because it's not straight away that things will work. We have to tune it for the required value of the input capacitance. So let's start with that. As we know that the whole thing is related to delay, and delay is not for one stage. We are not interested only in one stage, but we are interested, like let's assume that something like this. You may have, many gates like this, and then you want to find out delay from this point to this point. I'm just checking A to B path. So in that case, look, you cannot use Elmo delay. If you are using it, you can use it. It will also give the correct answer. The only thing is all of them has to be like, look at in terms of RNC, and you have to make the equivalent model, and then you can find out these things. But for one particular gates, it's okay, fine, you can do that. But for number of stages, you need to find out or devise a technique which is going to give you the accurate answer with lesser, hand calculation, which is required for the RC or required for the Elmo delay. So this is another technique for the number of stages. So it's not only for one particular gate. So let's start with that. So what particular linear delay model says? So please write down this in your notebook and remember, because we are going to use these equations many times. So what it says, D is equal to F plus P, where F is the stage effort or the effort delay. F is the stage effort, or you can say effort delay. I generally like to call it stage effort, so let's keep one name. By the way, these notations and other things are so much, you can say that standardized, that every book has same notations. The notations are not changing. If you are using Weston Harris, if you are using Rabe, or any other book like Kang or maybe Sutherland book, all book have same notations, same way. And P is the one which is the parasitic delay. So generally, when we are talking about such an inverter, there are till now you must have understood that what are the parasitics, like this is overlap capacitance, and all those capacitance will be there. So effectively, there is a big capacitor at the output and big capacitor as the input, right? So considering all together, let's call this one as C in and this one as C out. Notably, both of them are parasitics, so they are hidden, they are not visible, but you need to consider them at high frequency model, right? So this is what we are doing at high frequency, other than like it's reverse of what you are doing in analog, where you are making the low frequency model. Okay, so we understood that D, which is delay, so delay of entire circuit, is equal to F plus P, where F is the stage effort and P is the parasitic delay. Now going inside F is nothing but G times H, where G is the logical effort. Look at this. G is the logical effort and H is the electrical effort. Notably, electrical effort is the one where it's defined as like you have to drive a particular load value of the capacitance. So the ratio of C out by C in is going to give you the electrical effort. As the name rightly pointing out, electrical effort. So C out by C in. So C out by C in this case, C out has to be as low as possible so that you can drive that. In another word, H has to be less than 1 so that things will be pretty fine. But sometimes it's not happening. But there is another word for such electrical effort. We have renamed it actually, but the original name is fan out, right? So how much value of capacitance or how many input gates can be driven by particular logic gate is actually fan out or the electrical effort, as we have shown over here. Okay, there is one more thing which is logical effort, which we have not talked, but logical effort is going to be understood in maybe in next slide. So uh, here it is written that an inverter is defined to have a logical effort of 1. Or you can say that everything we are going to measure with respect to inverter. So let's make this as a standard, that inverter with respect to inverter we are going to make everything. What I mean to say that is, if you remember yesterday when we are talking about the logic gates, we learned that if this is the particular inverter where this is 1 and this is 2, these numbers are normalized with the W by L of NMOS, right? And if I want to make, let's assume that I want to make a NAND gate, right? NAND gate. So A and B, right? Okay, A and B. This is connected to VDD. So if I want to find out the values of the W by L, what I'm supposed to keep, it's in parallel. So this has to be 2 2. This has to be 2 2, but these two has to be 2 2 again, because 2 2 will give us effectively 1 and 2 in parallel to it's 2, right? Similarly, if this is not the case, if it is 3 input, like this, then all of them has to be 3, so that 3 is going to give me equivalent of 1. Here all are already in parallel, so this will be 2, right? So all these numbers are very important when we are going to find out the logical effort or the electrical effort, because C in C out are depending on these values. So this has to be designed such a way that you are designing an inverter with the fact that you are interested in you can say that TPHL, TPLH equal, or the switching threshold at exactly at middle. This is possible when you are doing such kind of ratio. Otherwise, this is not going to be achieved. So we are with expecting that we are making the W by L of any logic gate like this. Okay. So now let's just look at the electrical effort versus delay. Note that D is nothing but F plus P, where D is delay, F is electrical effort, sorry, stage effort, P is the parasitic delay, stage effort is nothing but G times H, where G is logical effort, H is electrical effort, where H is nothing but C out divided by C in, or it's also the fan out. Okay, so if I am drawing the electrical effort where H is actually changing, electrical effort is C out by C in. So as C out by C in is increasing, means C out is increasing. Let's assume that C in is same, but C out is increasing. Then what is happening to the normalized delay? So it's governing this equation. For right now, without deriving this, just I'm telling you that 3 input NAND gate, assume it for just for one slide that G equal to 5 by 3, which is logical effort. And electrical effort H is already known to us because it's on x-axis. Parasitic delay is actually, you can say that for as many number of inputs you have, that is the actually the parasitic delay. So if it's a one input inverter, then parasitic delay is always 1. If it's 3 input NAND gate, parasitic delay is 3. So these are the normalized number. Okay, so if you are looking for parasitic delay for inverter, then it's 1. So for inverter delay, I call it the inver. Then the G for inverter is 1. Let's assume that right now these values we can assume so that we can just understand the plot, and then we'll learn how to find out the logical effort. So 1 multiplied by 1 plus 1, that's going to give, or it's going to give me H plus 1. So with the offset of parasitic delay of 1, you can see that its inverter delay is actually rising with respect to the H. So the slope is H. But if you're looking at 3 input NAND gate, for a fixed logical effort, you will have the slope of H only, right? Sorry, with the slope of, here I made a mistake. The slope is 1 and slope here is 5 by 3, and the offset starting is actually 3 because 3 is coming from here. So this is from the standard line equations, right? So the most important part is as you are increasing the electrical effort, your delay will increase. So in that case, you can also understand that the slope will be G or the electrical effort. So electrical effort, logical effort. So logical effort is the important point because the slope is depending on G, and where G is the logical effort. Now let's understand what is logical effort and how it's going to be found out with these numbers. But before that, just let's understand one more thing. We want to make all the system PVT insensitive. PVT is nothing but process voltage and temperature. I believe we understood that. And we also understand that all intelligent engineers will use the approach of ratio. Means if I am doing this, I give guarantee that if this is R1 and R2, this is the ratio R2 by R1 plus R2. That is the value will be available over here. But if you are not taking ratio and if you are going with some other technique where only one resistance is involved, like the case in BJT, you might have learned that through which, like through this particular way, you can bias this also. But this is not a good way because it's not a ratio. The voltage available here, it's not in ratio, but it's depending on the resistance which is changing with respect to the temperature. So this resistance is changing with the temperature, right? So there is some plus or minus values are there. So which is changing the current. We don't want that. So we are keeping one resistance over here so that it's in ratio. Let's say R2 and calling it R1. So here, whatever the voltage is coming, it's in ratio. R2 divided by R1 plus R2 times VCC, right? So it's always a ratio, and it's going to give you the required value. Even if there is a temperature, if R2 is varying by so much percentage, R1 will also change by that much of percentage, so that you can have the ratio remain same. So this is also the fact for capacitor. This is also the fact for transistor. So what generally we are doing, we are calling some term called matching of the transistor. When we are saying matching of the transistor, what does it mean? Let's assume that I want to make an inverter like this, whose W by L are as follows, like 2 micro divided by 120 nano. This is 1 micro by 120 nano. Okay. If I am connecting maybe similar inverter, but now I'm interested that this value to be 4 micrometer, or this value to be 2 micrometer, like this. So here you can see that the ratio is 2. Instead of this, if I do as follow, like 2 micrometer by 120 nano and 1 micro by 120 nano, which is exactly identical to what it was here, and I'm keeping one more transistor in parallel with, note that these two gates are shorted. So 2 micro by 120 nano, and same thing is going to be happen over here. In this case, as we have learned that two transistors are in parallel, then width is getting double, right? So effectively, it's equivalent of 4 micrometer divided by 120 nanometer, and this is 2 micrometer divided by 120 nanometer. Look, in Cadence or in Simica, you don't have to do all such things like this. What you have to do is, when you are going to press the Q is the property. There are various parameters are given, like width, length, and many others, but you need to find out M. M is the multiplier. When you are pressing the multiplier, what does it do? Let's assume that I am keeping multiplier 2, and this is 2 micro, and this is 120 nanometer. It's actually like this. So my simulator tool is going to keep two transistors whose values are 2 micro and 120 nano in parallel, right? When you are using the multiplier, notably this multiplier option is available in Simica, and like the paid version of Cadence and all, multiplier is always there. You can use that. The name of this one is just M. Similarly for capacitor, similarly for resistance, everywhere M is available, which is multiplier. So that many transistor or resistance capacitance will be in parallel. But now there is one more thing which is only available in paid version of Cadence. It's known as fingers. So when it's a multiplier, you are adding so many, like its equation is very straightforward. That multiplier multiply by W by L, whatever you have given here. So it's actually M times W and L which you have given. But when you are doing this, you are okay. Before going to fingers, let's complete the multiplier completely. So what it does, I'm keeping so many transistors in parallel like this. I'm drawing the layout, by the way, for your information. So such M transistors are in parallel. I'm connecting all the gates together, all the drains together, These are the drains and sources together. So like this. So you have all the transistors in parallel. Look at this. There are M transistors in parallel and the connections are as follows. But when you have the fingers, it's little bit different. Similar to multiplier, any one of the input you can take. But the finger is the one where the transistor looks like this one. It's very simple one. So it's a big transistor where if you have seen the main building of IIT Delhi, it looks like this one. There are many vertical stacks are kept like this. Each one of them is known as, by the way, fingers. So if you have n number of fingers, means n number of gates are there and all are tied together and making them gate. Notably, if one side is source, other side is drain, and drain is actually overlapping from both sides. Again, source is also overlapping and it's takes the area from both sides. Source, drain, source, drain, source, drain. Here in multiplier, it was not there. Look at this. This space was empty. Of course, you can keep one on top of another one and look alike what is happening here. But that is what multiplier does. But in the case of fingers, when you are giving this, what exactly simulator understand is if W is, let's assume that 2 micrometer, length is 120 nanometer, and if you are writing fingers, generally it's given as F in the simulator. Unfortunately, that is not the part of Simica, so please do not find out in Simica. It's available in Cadence. When you come back here in the on the campus, you will see that in Cadence we have fingers. So if fingers are equal to F, or let's say for this case, let's assume that it's 4, then what is happening, this is the length, by the way, and this is width. So when you are giving this value, it's actually for total, for all the finger, all the width. What I mean to say, there is one more word you can find out in Simica, width per finger. Means width per finger means one finger will have a width of whatever the width is given to you divided by F. Means in this case, it's 500 nanometer. So by giving fingers of 4, the W by L is still 2 micrometer by 120 nanometer, but each one of the finger having the width of 500 nanometer. So 500 nanometer, 500 nanometer, 4 are in parallel. So it's like this. If you are looking in terms of multiplier, right? Because it's getting multiplied. But here, in the case of finger, it's getting divided. So this is the fundamental difference between finger and multiplier. So please note that we are going to use it whenever you will be here back. And for a time being in Simica, you can use multiplier. So the option of multiplier is there in Simica. But that option tells you that it's 2 or whatever the number you are going to multiply, that will be there. And here, why we are doing all these things? Because look, once you made one transistor whose size is, let's say, I can say that I am declaring that as a unit size of NMOS, and this one is unit size of PMOS. So just I am going to do the control C and control V. I'll keep here I'll keep so many transistors in parallel by using the multiplier or by using the fingers. When you are using the finger, you have to make sure that you have to write down the same value of the W and L which you want, but with finger of 2. When you are using the fingers of 2, it's actually width per finger is 2 micrometer, which makes the compatibility with 2 micrometer or the unit size of PMOS and NMOS. So this is what generally we are doing, and this is what I meant for the matching of the transistor. Matching of the transistor will use the fingers or will use the multipliers. So this is fingers F and this is multiplier M. Using this, like you must have heard about the FinFET. So instead of having only one gate like this, so I'm drawing the ideal one. That's why this is matching everything, right? So instead of having such kind of structure, what they are saying doing, they are making small fingers like this, and all the gates are actually tied together. These are the gates. So in FinFET, the good part is like when they are connecting the making the electrical connection, what they are doing, they are making like this. So if you have seen the chocolate called Melody, so inside the chocolate and then outside is some brown part is there. So it's like this. The connection is here. So if I'm feeding some electrical connection over here, or if I'm giving voltage here, the electrical field is going everywhere. Look at this. Entire gate is having the electrical field. In this way, the current can reach faster, or you can say that the faster transistors can be achieved. So speed wise, it's very good. This technology is by Intel, by the way. So they are using this FinFET. But the only problem is when you are making such a small technology like 7 nanometer. To make small fins of, let's say, if you want to make 1 nanometer each, it's very difficult. You might have many more second order effects. So that technology at the smaller technology nodes has to be proven in terms of fabrication. So that is not known to us till now, or Intel is working on it. Maybe they will give us some good technology very soon. So this is about FinFET, and that is what we are using, and we make sure that all the transistors are matched. If they are matched, so if one transistor has an error of plus delta or minus delta, same will be waved off because of the approach of ratio, right? If you are making any kind of things, and this is very much popular also in analog designing, rather than I would say that it's in digital. But in digital, when you want to have equal switching threshold, equal delay, and everything, you want the matched one, then you have to use the ratio logic, which is using fingers and multipliers. Okay, and this is already known to you. Two transistors in like this series, its L is double, and if you are having two transistors in parallel, its width is getting double. Okay, so this is what you are doing in terms of multiplier. Okay, so now let's get back to the real business, where you understand that G is nothing but a logical effort. So we assume some value earlier, but now we are not going to assume. Let's understand how it works. What we are doing here in logical effort is we have to keep the reference of inverter. Inverter is a reference. We learn that NMOS value is equal to 1 and PMOS value is equal to 2. This is with the fact of mu and mu p ratio. Same thing you can find out with the simulation by connecting these two together. By varying the p width, you can have the value of the required p width where both the resistances will equal. As I'm using West and Harris, they are taking the ratio of 2. If you are looking at Rabe, they are using the ratio of 3. But all the way, they want to say one thing, that with a particular ratio, you will have both the equal resistances, and at the output you will have VD by 2 output when input is also VD by 2. So for that, this number might be changed because it's depending on the technology. So let's assume for Weston Harris book, they are using throughout the book 2, and most of the time when it's Rabe, they are using 3. Okay, and in Simica it's 1.55. So now we have to look at following things. If I am looking into this inverter, you can count on these values 2 and 1. Notably, when I am seeing in a branch, there are two capacitances, one having 2 and one having 1. So if I'm having the branches, they are in parallel. Because of the parallel combination, I can say that they are going to be added, right? So this side is C1 and this side is C2. C1 is 2 and C2 is 1. So at the input side, this is input. So I can say that the input capacitance of this inverter gate is equal to 3. It's addition of 2 and 1. Okay. There is one more thing. As an inverter, it can only drive same inverter because we have designed for it. If these ratios are changed, it cannot drive it. Or when I'm saying it cannot drive, means the output will get like this. You can see the rise time and fall time, or it's possible that it's not reaching the required value if these values are increasing. So I'm saying that for the input capacitance of 3, I can drive only the input capacitance of 3, right? And that is what I'm going to call it logical effort. So instead of this, if I have like this, if I am following the Rabe's book, let's say, where this is 1 and this is 3, what I can write down, input capacitance is 4, which can drive same input capacitance, which is again 4. Notably, ratio remains 1. Look, if you are changing the technology, the ratio remains 1, where G is the logical effort. I am finding out the logical effort. Note that. So the ratio is 1. Either you are taking 1 and 2, 1 and 3, or maybe with the Simica, which is coming out as 1.55, then this will be equal to 2.55 divided by 2.55. Still the ratio remains same. So the logical effort of an inverter is equal to 1. That is what we have taken over here in the plot. If you remember, this plot has G equal to 1. Okay. So G remains same. The ratio is 1. Okay. Now I'm changing this. Now I'm changing this to different gate. Let's assume that I have this gate where inputs are as follows. So I know that with the Weston Harris understanding that the ratio is 2. So if I want to make these two as 1, I need to make 2 each, so that the series combination is going to give me 1, right? And here for the making the ratio of 2, I need to keep both of them 2, right? By the way, this is a NAND gate. Now I need to find out the logical effort of such circuit. So in that case, G is going to be, note that I'm looking only for one input. Right? Something like this. So there are two inputs, one is A and one is B. So in A and B, you have to take care of only one. So in that case, if you are looking here, 2 is here and 2 is here. So if I'm looking at the one input A, the effective capacitance is equal to 4. Any one of the input you have to take. Notably, you will get the same answer, by the way. If you don't get it, then you have to cross check it, because that's a sanity check that your answer is correct or wrong. So Cin is equal to 4 over here. And we are doing this everything with the fact that we are going to drive the load which is having the ratio of 3. Means we are designing everything to drive the ratio of inverter. So the input capacitance of inverter is 3. So we are going to call it 3. Note that this number is coming with the fact that you are making the ratio of 1 and 2. If the ratio is 1 and 3, this becomes 4. This will also change, by the way. So in the case of a NAND gate, the logical effort is 4 by 3. But if I change a bit, like if it is 3 input NAND gate like this, then all of them will be 3. Let's make it with the better color. Like if all of them are 3, all of them are 2, with the fact that the ratio downside is 1 and top side is 2. They are in parallel, so we don't change it. But because of series, they have to be like this. So any one of the input you can choose. So input capacitance is equal to 5, which can drive the inverter, which has the input capacitance of 3. So 3 input NAND gate has 5 by 3. Let's go with this one. So I believe this is not required the repetition of what I said. But for 4 input, it's going to be equal to 4 by 6. Sorry, I made a mistake. It's going to be equal to 6 by 3. Right? And similarly, you can find out more. Like 5 input is going to make this one 5 and 7 by 3. You can find out some equation also for NAND gate. Note that we are making for NAND gate because it's an universal gate. That's why we are doing so much on NAND gate or inverter, which is the one through which we are finding out other ratio and other things. Now, next universal gate is NOR gate. So now let's assume that if it's a 3 input, I know that the downside which are coming in parallel and upside which is coming in series in the CMOS technology, I know that any one of the input I can pick up. The input capacitance is 7 and it can drive the inverter input capacitance of 3. Let's try for maybe 4 input NOR gate. So 4 input NAND gate A, B, C, D are the input. A, B, C and D are the input. So ratio wise, this side, as we have seen here, all were 1 because we want the ratio of this side is 1, but all are in parallel, so we are going to keep it 1. Upside 4 are there, so we need to keep all of them 8, so that when you divide it with 4 transistors, it's going to be equal to 2. In this case, the input capacitance on any of the input, it's equal to 9 divided by the driving to the inverter, which is 3. So the answer is 9 by 3. Maybe you can think about some equation. Look at this. So there are inputs are n are the inputs. So 3, for 3 inputs, it's making 7. So can I write down this 2n plus 1 divided by 3, where n is the input. Let's see whether it's matching over here or not. So it's 2n plus 1 divided by 3. This will match. 4 inputs are there. So 8 plus 1, 9 by 3. But if you are looking at NAND gate, look, this will not work for 2n plus 1 by 3. Because 3 inputs are there. So it's not 7 by 3. It's for the case of NOR. So not NAND has to be something else. What does that that would be? It would be n plus 1, 2 by 3. 3 will be the fixed one. So if the inputs are 3, it's 5 by 3. If the inputs are, let's say, 2 inputs are there, no. If there are 2 inputs, I know that the answer has to be 4 by 3, right? Because 2 will be 2, 2. It will be ground over here. So 4 by 3 has to be answer. Whether it's matching or not, we can check. 2 inputs, so n will be changed to 2, and 2 plus 2 by 3. If the input is changed to 5, this will become 7 by 3, and so on. You can see the equation over here for NAND and NOR, because these are the universal gates. That's why we are deriving. For other things, those are not required, or you can say that those needs to be checked because it does not follow any equation, right? XOR, XNOR. But look, if you are like working with NAND and NOR, things are pretty fine, right?